Okay, so yeah, do this. I guess you could maybe. He's worth a lot of money now. So this was the outline of what we're going to do today. Okay, so paths and graphs. We're going to look. We already figured out a way to do paths and graphs, right? We used depth first search to figure out whether nodes are connected, right? And so. Okay, so here's a set of paths, and we want to find the shortest distance between two nodes here. Okay, whereas depth first search allowed us to tell us whether two nodes were connected. Did it tell us? The question is, how do we find the shortest distance? Okay, so let's try depth first search on this graph. Okay, do you think it's going to work? Well, let's try to find the distance between S and S is a source vertex. We're gonna start our depth first search at the source here, which we'll name S in this example. So, what do you think? You think depth first search will find a short path from S to C, say? Yeah, well, it might not. It depends on how it starts. It does find it for C because I didn't do it in lexicographical order, but it doesn't find the shortest path from S to A. Right? This is what depth first search would do. Remember, depth first search, let's just say it first explored E, and then from E it could explore D, and from D it has no outgoing arcs to anybody who's not already explored, so it pops out to E, it pops out to S, and then from S it goes to C, and from C it goes to B, and from B it goes to A, and then it pops out. So it did discover a path from S to A, but the path was not very short, right? There's a much shorter path. Do you see the shorter path? Right, there's a path of length 1. It's also true for D. It did not find the shortest path to D. It found a path to D, but it did not find the shortest path. Okay? Does that make sense? Okay, so algorithm 2. So we're going to try another algorithm. Depth first search didn't work, so we're going to try picking it up. We're going to assume that these things are sort of strings or something, okay? And so that's why they're all squiggly. And now I'm going to pick it up by S. I'm going to hang it by S. Okay, that worked better, right? So S, I pick up S, and the guys that are next to S sort of come up a little bit higher because they're directly connected. And then the next level is those that are connected to the second level. Right? So there's a sort of natural algorithm for finding the distances. And here, the distance from S to E, D, A, and C is 1. So that's the first level. Or the first level is S. What's the distance from S to S? 0. So the first level is S, or the 0th level is S. Then the next level is E, D, A, and C. And the next level is B. And there is no shorter path from S to B. Right? Is that clear? The shortest path in this graph is also 2 steps. So it's also the leveling that's produced by this picking up algorithm. Okay? Okay, so now, so these are the distance 0. The way the leveling algorithm works is there's a distance 0 nodes, and the distance 1 nodes, and the distance 2 nodes. Okay, so we proceed layer by layer. You can think of the picking up process as proceeding layer by layer. You pick up the S, and eventually some other nodes come with it, and those are the neighbors of the 0 nodes, and those are the ones that come out with S. Okay, and those are the distance 1 nodes. And then as you pick it up higher, you know, the distance at D nodes pick up the D plus 1 nodes, right? So you can sort of get these in this order. Okay? Yeah, if all the edge lengths are the same, it wouldn't look like this. It wouldn't be spread out like they're not the same. They would all be along the line. But the order in which they came off the table would actually tell you the breadth first search distance, right? 0, 1, 2. And all the ones that are 1 come off at the same time if these things are the same length. Okay? So this is an algorithm. So it's not a very good algorithm for a computer, right? In a computer, you're not going to take your graph and wire up these strings and everything. So what should you do instead? Okay, what do you think? Yeah. What? He's jumping ahead. He's saying he said Dijkstra's algorithm, but we're just these edges are we're just trying to think of a very simple case where they're all length 1. We're just trying to figure out the least number of hops from S to each one of those. So yeah. Yeah, so in some sense, with the depth first search, we did use a data structure. We used a stack. Okay, the explorer was saying, who do I explore next? Oh, okay, let's look on the stack and pull something off the stack to explore and then and continue. So here we're going to use a queue. So we're going to use a queue. That's what he said. He said use a queue. So the queue, the reason you want to use a queue is what's first? S. Okay, so you put S in a queue and you take it out. That's not a big deal. That's trivial. But now from S, you put all its neighbors. You look at all its neighbors. And whenever you see one of the neighbors, you put it in the queue. Okay? So remember, in this picking up algorithm, what we're doing is we're saying, well, S gets picked up first. Okay? Then all its neighbors get picked up second. And nobody else gets picked up for a while. As you move it up, S is sitting there, nobody's picked up, and then once it's high enough, you pick up all of S's neighbors. Okay? So once that happens, you put them in the queue. Okay? And then you throw away S, and then you start picking up them. Right? You pick them up in order, and as you pick them up, you're going to pick up the next level, which is the distance 2 nodes. So you don't want to start picking up a distance 2 nodes separately from a distance 1 node. You want to process all the distance 1 nodes first. So since you saw them first, you put them in a line, and that's what a queue does, right? S tells you what the neighbors are. You put them in a queue. Now, for each of their neighbors, you process their neighbors. But then you don't continue with their neighbors. You go to the next one at distance 1, and then you go to the next one at distance 1. Okay? So this is what depth first search does. It starts where it says the distance to the source is 0, which is by definition, and we say we just mark it as whether we visited it before or not. This should be something that's familiar from depth first search. Okay? So now you put S in the queue. We're going to have a queue. And while this queue is not empty, while we keep getting something out of the queue, for each of the neighbors, this is what this says. For each outgoing arc from you, if V, it should be visited of V. If visited of V is false, then visited V, we're going to set visited V to true. We've now visited this node V. And we're going to set distance of V to distance of U plus 1, right? Because we're processing a node at some distance, and now for each one of its neighbors, we're going to say, okay, you're 1 higher if you already don't have a distance. Okay, if you're not already off the table or in the queue, I'm going to say, well, I discovered you, so I know the distance to me is D of U, so the distance to you is at most D of U plus 1. Right, because you could always go through me and take one more edge. Okay? And then you put V in the queue. So each level is explored in order. So that's why this is correct. Okay? So you need to argue that each level is explored. You explore all the 0 nodes. Then you explore all the 1 nodes. Then you explore all the 2 nodes, and so on. Right? That's what needs to happen for this to be correct, because when you explore the 0 nodes, you label if you explore all the 0 nodes first, you know you've labeled all the 1 nodes that you need to. They all have the correct label because they're neighbors of the 0 nodes. Now, in general, if you explored all the D nodes, you know you've touched all the D plus 1 nodes, because from the D nodes you've explored all their neighbors. And a D plus 1 node must be a neighbor to a D node, right? Okay, so this is what so S is explored, right? That's just trivial. You put it in the queue, you take it out of the queue. So it's explored before everything else. So after S is explored, the queue, we're going to use this inductive property. The queue has all distance 1 nodes. When you're done exploring S, which is the 0th level, you have the whole 1 level. Okay? You have all the 1 nodes in the queue when S is explored. Okay? Okay, so now when the last level D node is explored, when you're done with the level, what you want is a queue to contain the next level. You really want it to say, well, what's the first level, what's the second level, what's the third level, what's the fourth level? You want this level by level exploration. And we're saying, once you finish exploring the last D node, D level node, what's in the queue? What are the nodes in the queue? Are there any D plus 2 nodes in the queue? Okay, this is important. You know, I could just tell you and you can sleep through it, but it's better to figure it out yourselves. He said no, and he said because, now you think about it, right? Are there any D plus, once you've processed the S, are there any distance 2 nodes in the queue? No, because you haven't processed any distance 1 nodes. And before you can reach a distance 2 node, you have to process a distance 1 node. Okay? And the last level, maybe we should put the lights on the audience. Do you think we can do that? Oh, yeah. Okay. So, okay. Does that wash out the screen? Is this okay? Okay. Is this not okay? It's okay. Okay. So that's fine. Okay. So, okay. So now, so just think about this. When the 0th node is, when I've processed it, all my neighbors are in the queue because they're level 1 nodes. And I haven't taken anything else out of the queue. And none of their neighbors are in the queue. And those are the level 2 nodes because I haven't processed any of them. None of their distance 2 nodes are in the queue. Of course, I'm one of their neighbors. Okay. So I thought when the last level D, so this has to be parsed correctly, right? This is English, an English issue, is when the last level D node is explored, the queue has all the distance D plus 1 nodes. Okay? And why is that? There's no distance D plus 2 nodes yet because you haven't processed any D plus 1 nodes. You can't see a D plus 2 node if you haven't processed a D plus 1 node. Okay? And all D nodes in the queue are before any D plus 1 node. Right? That's by, what is that by? By induction. Right? Because when you process the D minus 1, the last D minus 1 node, you know that all the level D nodes are in the queue. And no D plus 1 nodes are in the queue. So you know all the level D nodes are before any D plus 1 node by induction. Okay? Okay, so this is an inductive proof of the correctness of breadth first search. Okay, so this thing is, I'm being picky here. I'm being opportunistic. I'm looking at the queue at specific points in time. Like at various times, there's actually 2 little different levels that may be in the queue, D and D plus 1. But I'm saying at least at this point, it's all good. Okay, and this property then is good enough. That's all I need inductively. Okay? I'm saying at a certain point in time when I've processed the last D node, only the D plus 1 nodes are there. So it's an induction. But it's not an induction on every queue operation. It's an induction at various points in time in the queue. So it's just these graph algorithms, when you see them and you read them quickly, you're like, oh, yeah, duh. But to set up this induction, actually the people who wrote the book were clever about it. Okay? So in general, you have to be a little careful. So some of the arguments are subtle, even though they're almost always quick and not necessarily painless. But, okay? Okay, so let's see it in action. So this is, let's just review it. You mark it true. I have the typo here again. That should be visited of V. Once you're looking at V, the visited of V should be, if it's false, then I set it to true. And I mark I mark the distance to the new node that I just discovered as one more than the node that I'm going from. Right? And then I put V in the queue. Okay, so let's start. The queue has S in it. So we're going to start on that graph. So we don't even have any notion of the graph. This is really what the computer sees. It sees nothing, right? It just gets this name S. Now, once it has this name S, it can go and look up the node S in your graph representation. Okay? So now that's what the computer sees. It sees nothing in the queue, and it's looking at it has a handle on the node S. When it has a handle on the node S, it can look at the neighbors of S. So it looks at one, it's not in lexicographical order in this case. It's the first neighbor is E. When it discovers a node E, it sees that it's not visited. So it marks it as visited, and it sets its distance label to 1, right? D of S is 0, D of E is now going to be 1, and it puts E in the queue, right? So this is what the computer has again. Now it has these two nodes, and now it can look at D. It looks at the next neighbor of S in its adjacency list, which is D. It puts D in the queue through the same loop. And then it puts A and C through this 2 more times through the loop, put A and C in the loop. Now S has no more neighbors in this graph, so what does it do? We pop out of this loop, right? We're done with the edges here, and we extract the node from the queue. That should be extract. Okay, so I take E out of the queue. So now I'm going to start exploring from E. Okay, and E has one edge outside of it that has not been visited. That hasn't already been seen. It sees D. D is visited, so it doesn't do anything, right? It simply doesn't go into this loop because D has been visited. Okay, so it has this funny. So there's arcs that go from a level to another level, and there's arcs that go between the same level. Those are so far we've discovered 2 kinds of arcs. There's arcs that go between a level, the tree edges in this case, the breadth first search tree edges, and then the cross edge. We have a cross edge between the same level. Okay, so that's another kind of edge. Okay, so now there's no more arcs to explore out of E. Now we look at D. D looks at its neighbors. Both of them have been visited, so there's nothing to do for D. Now we pull A out of the queue and we start exploring it. That's why it's highlighted in red. Okay, so it sees an edge to B, so it finds a new vertex. It marks that one as visited. It sets its distance label to 1 more than its own. Its distance label is 1. That guy's distance label is 2. Okay, now I'm done processing A, so now I start processing C. Now again, C looks at its neighbor B, and it sees that it's seen B before. I mean, that the algorithm has seen B before. So there's another kind of arc here. So the blue edges form a tree, and the red edges don't. And there's 2 kinds of red edges. Ones that go between the same level, and ones that go between successive levels. Can there be an arc that goes from S to B? No. Right? That's a property of breadth first search. If there was an arc that went from S to B, then B would be in a different level. Okay? So these are what the tree edges look like. The tree looks like the blue thing, where every blue edge goes from level to level. And there's also other edges which are not in the tree, which are always either within a level or between adjacent levels. Every edge is either between an adjacent level or within a level. Okay? In breadth first search. Even the tree or the non-tree edges. Okay? So are there any questions? Okay. Okay, so, and that's the end. I guess B was in the queue. Now we explore from B, and we're done. Okay, so we know that's correct. The running time, again, how often do you look at any node? You remove it from a queue once. And each time you remove it from the queue, you loop over its adjacency list. So this is a linear time algorithm, just like breadth first search, just like depth first search, right? So again, you charge it. You charge this piece of work to an edge. So each edge may be explored from both sides. So that's 2 times the times that you go through this loop. Okay, so it's a linear time algorithm. So it's fast. It's good. Okay, so now the question is, what about edge lengths? Can we use breadth first search for edge lengths? Well, if we want to go from San Francisco to LA, it's only one hop. So we just look at the one hop path here, and we say, oh yeah, well, yeah, that's the fastest way. It does happen. If I just run my breadth first search algorithm on this graph, it'll work for San Francisco to LA because it's one hop, and I look up the length, and that is the shortest path. Okay? How about San Francisco to Las Vegas? What's the shortest? If you do a breadth first search on this, what would the label of Las Vegas be from San Francisco? 2, right? It's 2. The label will be 2. So it's 2 hops in this graph. If you so just ignore the numbers, and it's 2. And in fact, there is a shortest path. This is the shortest path, and it's 2 hops. It is indeed 2 hops. Okay, so you can use breadth first search. Well, you can kind of use it because there's actually 2 hop edges here, right? So this is also a 2 hop path. There's no reason breadth first search will output the blue path versus the red path. Okay? If you build a tree from San Francisco to the rest of the graph, maybe these red edges will be in the tree rather than the blue edges. And if the red edges are in the tree, the path you find in the tree between San Francisco to Los Angeles to Las Vegas will be the wrong one. Okay? So breadth first search is really and let me just really make this point again, okay, with Reno to LA. What's the shortest number of hops you can get from Reno to LA? 2. So breadth first search here would definitely find this path. Not only could it make a mistake, it will absolutely make a mistake. Okay? Because the shortest path in terms of total distance is to go through Sacramento and then San Francisco and then to LA. You know, especially Las Vegas, you could just stay there, right? There's problems with Las Vegas. So there's some probability of not leaving. But we're not modeling that. So it's not 2. So breadth first search definitely does the wrong thing. There's no way you can say, well, you know, I can be clever about how I choose the edges. The algorithm's properties make you do the wrong thing for when you have numbers on the edges. Okay? So how do we fix that? Oh, you guys are just jumping way ahead. You guys did Dijkstra in 61B, right? Well, we're going to do it again. Okay, but it's going to be, we'll do it a little differently. We often repeat stuff, like we do hashing. Here we do hashing more formally. We're going to do that sort of same thing. That's the way that we reinforce. So, okay, so the length of the edge is L of E. So I'm just defining the problem formally. So what you're given now is a graph. G equals V, a set of vertices, a set of edges. For each edge, you have a length now, instead of it just being presumed to be 1. Okay, so this is an example of a graph. And so what's one way I might solve this problem? Okay, Dijkstra, but we have breadth first search. Is there a way I can force breadth first search to solve this problem? Yeah. Right. Okay. Yeah. So he said make a new graph with where you put nodes, like for this edge here, the length is 7. So he's suggesting putting 6 fake nodes in the middle. Yeah. 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 Well, we're going to do that in a few slides. This is like I agree we could do that, but try to think of it this way, because this is a really beautiful way to think of it. I agree. I think I looked at the slides for 61B. I think sort of seeing it this way is really sort of nice in the education. When I first saw Christos, I work on shortest paths. I have papers on shortest path. But when I saw Christos first explain it this way, I was like, wow, that's cool. So think ahead, but also don't ignore this. So I think it's beautiful. So okay, so yeah, I mean, because then it becomes obvious, right? It's not like, oh, priority queue, oh, there's this fancy thing going on. Let's just go step by step and we'll get there. Okay, but I appreciate that. That's a good answer. Okay, so this is what he said to do. He said replace with the length L of E path, right? So we're replacing this edge with a path that takes 7 hops to traverse. Okay. That one is 4, so it takes 4 hops to traverse that one. You know, and so on. Okay. So then what do I do? Now I can run breadth first search. Now it's essentially the distances to the nodes here in this modified graph are the distances that I was looking for in the original graph. Okay? So again, this action of a priority queue is just really simulating breadth first search. Dijkstra is really simulating breadth first search in some sense. And we're going to get to how it does that. But here we could just run breadth first search, see? So there's breadth first search. It explores all the level 1 nodes. It explores all the level 2 nodes. I wrote the distance label on A here because it realized it got to a real node and it wrote down the distance label. I'm just outputting it. Now you go to the level 3 nodes. Now you go to level 4 nodes. And again, you see this property. There's a 1 hop in the original graph. There's a 1 hop path to E, but the shortest path takes 3 hops, right? But on the hand, in this modified graph, everything is kosher. Okay? Okay, so that's the nice thing. Now I don't need to argue about its correctness. I already argued about it. It's a breadth first search. The reduction is fine. The paths have the same length. Okay, that's one nice thing. Okay, so what's the running time? Well, the running time, that's not so nice. It's the sum of the edge lengths, which doesn't seem so bad, right? It's just the sum of the edge lengths, right? So let's see whether that's bad or not. I think it's very, very bad, and this is why I think it's very bad. Let's think of this problem. I have 2 nodes in my graph, and the distance between them is 1,000,000. Okay? So what's the size of the representation? And this goes back to this original problem and the basic concept of who we are as computer scientists, right? We talk about the size, when we talk about the size of a problem, we don't say the size of this problem is 1,000,000. What do we say the size of this problem is? Well, there's 6 digits, I guess 7 digits to represent this number, right? So the size of the problem is about 6. That's what we as computer scientists think of as the size of the problem, is how many bits does it take to represent it. We're not Romans, right? We have a place value system, right? Well, maybe we are Romans, but I mean we're not ancient Romans. So we're not restricted to have this a long representation for big numbers. We have short representation. So the size of this problem is about 6 or 8 or 10, some sort of smallish number, right? But the time is 1,000,000, right? We put those dummy nodes in the middle and we do breadth first search and we wait 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 and then eventually it finishes. Okay? So while it's really nice to sort of phrase this problem this way as, oh yeah, it's just breadth first search in this certain with a certain point of view, but with this reduction, it's not effective in terms of running time. Okay? So it's 1,000,000-ish, I guess. Okay, so the distance is, and the distance is obviously 1,000,000, right? In this example, oh yeah, it's 1,000,000, right? I didn't even need to think about it. Okay? So well, in some sense, why didn't I need to think about it? Well, if I look at it, I can just think about, okay, so well, I can just look at it and say it's 1,000,000. Or I can think about the reduction. I can put the 1,000,000 nodes on it, and I can say, well, what's breadth first search going to do? It's going to explore the first dummy node, and from that dummy node, what is it always going to explore? The next dummy node. And after that, what's it going to explore? The next dummy node. And actually, I know what's going to happen for the next 1,000,000 steps. It's just going to keep going to the next dummy node, right? And at step 1,000,000, what do I know is going to happen? It's going to get to B. So I can see the future, right? That's the key here. I can really see the future. I see something significant. When is something significant going to happen? Well, not for a million steps. I know that. When I start down this path, I know nothing's happened. I can see clearly now. So it could be easier. So let's see. Let's see the sort of setting again in this setting. So okay. So here's another example. Let's just watch it. Let's go ahead and do our breadth first search reduction. So we have these nodes. Okay, there's the node 1, there's node 2, there's node 3, 4, 5, 6, on and on and on, right? Nothing's happening. Each node is just queuing up the next node, and that next node is being pulled out, right? Nothing. When is something interesting going to happen? Do we know when something interesting is going to happen? At point 20. At 20 steps, something interesting has happened. We know that. So what should you do? Just wake me at 20 steps, okay? Okay, so that's what we should do. We know nothing interesting is going to happen. We can sort of see, well, okay, the first real node, you know, when I look at A, I look at C, I see that I have an edge of length 20 and I have an edge of length 30. And I say, well, nothing's going to happen for 20 steps, right? I know I'm just going to sort of explore these dummy nodes for 20 steps. I'm just not going to, what I'm going to do, and you know, but I know what is going to happen at 20 steps is C is going to pop out of the queue, right? It might pop out earlier or something, and I know that at step 30, before step 30, B will pop out of the queue. But certainly C will pop out at 20. So I say, well, okay, I'm not going to worry about exploring dummy nodes. I'm going to pretend they're being explored. Because I know if I explore the dummy nodes, at time step 20, out will pop C. Okay? So what I'm going to do is I'm going to pretend I explored all these dummy nodes and just not really do it. And just at time step 20, I'm going to wake up, I'm going to come to work, and I'm going to say, hey, C is here. You know, my boss is expecting me to pull these dummy nodes. I'm not doing it. I'm just coming out and say, hey, C is ready. Okay, at time step 20. I set myself an alarm. I say in 20 time steps, I'm waking up, I'm putting C up. And then I'm going to explore C then. That's what the breadth first search algorithm would do anyway. Right? At time step 20, it would explore C. Okay, and then, so that's what I'll do. So let's see if we can turn that into an algorithm of how we process these things. We set our alarm clocks. We wake up at the appropriate time. We do the appropriate thing. And the appropriate thing will involve setting more alarm clocks. Okay? So for edge AC, so processing A means you look at all the adjacent edges. That's what the breadth first search does, right? It looks at the adjacent edges. So what it does is it sets the distance, just for now, as a temporary thing. It sets the distance to C. Look, I've discovered a path to C of length 20, so that's what it does. It sets that. And it sets an alarm for 20. Now I'm setting an alarm clock, because I know at time step 20, C is going to pop out. Okay. Or maybe 20 or sooner. It might even be sooner, but definitely for now, it's, you know, if I'm only going along this edge, it's not going to be sooner than 20. Okay, now for edge AB. So I look at that, and I set D of B to be D of A plus 30, right, because D of A is 0, right? It's 0, so it's 30. So I set it temporarily. I say, well, I found a path of length 30 to U. So I'm just going to mark it down, just do some bookkeeping. But I'm going to set an alarm for 30. I know by time 30, I better be looking at you. But right now, I don't have to worry about you before that. I don't have to worry about B. Going across this edge is not going to do anything for 30 time steps. So I'm not going to worry about the alarm clock for that, for 30 time steps. I'm going to go check on B at that point in time. Okay? So now I don't do anything for 20 steps. Nothing. No work at all. Okay? So, but at times 20, I wake up. So far, what have I done? I've processed 2 edges. I haven't done anything for 20 steps. I've only done it for one step. I've only processed 2 edges. Okay, breadth first search, I would have been working that whole 20 time steps. Okay, so now for edge E, for edge CD, now I set D. Now I haven't seen D of this node D before, so I set the distance to D to be, this is a temporary distance label, to D of C plus 3, which is 23. Okay, and that's what I show in the blue up there. And now I set an alarm for it. I say, okay, well, in 3 steps, if I cross this edge using breadth first search, I will see this node at time step 23. So let me just set the alarm. Okay, so for edge A, B, now something interesting here happens for edge A, B. What's interesting here? Oh, crap. Okay. For edge CB, I need to get a touchpad. Okay, so let's see. This won't work, right? Okay, so, okay. For edge, oh, this is the most interesting edge. All right, okay, so for edge CB. Okay, what happens for this edge if we look at the graph? So right now, oh, we've seen B before. Okay? We've seen the node B before. So normally we wouldn't do anything with it with breadth first search. But here we're doing something a little different. We've seen it, and we see that its distance label currently is 30. But we know that if we go through C, my alarm clock says 20. My value right now is 20. In 4 more steps, I reach B. Okay? So D of C plus D of BC is equal to 24. So now D of C says, well, that's how long it took to get to C. And I know I can get here in 24 units. And I really, so if I was doing this by breadth first search, I would actually be processing this node B at time unit 24. That 30 time unit, that other path, would just be somewhere in the middle of this path or toward the end. It would be 24 units down on this path. It wouldn't explore to the end. Before I got to the end of this path, I would already have gotten to B using my breadth first search. So I better reset my alarm to actually obey what breadth first search would have done. And breadth first search would have gotten to C, and then in 4 more steps, it would have gotten to B. Okay, so I have to, if this alarm is too high for B, I reset it to be lower. Okay? Okay, so this is exactly the case that this is the subtlety in the San Francisco graph too. What I've discovered is a path of 2 hops, which is shorter than a path of 1 hop. Okay, that's what this is exactly doing for you. This step is what's allowing you to be able to use, find shorter paths that actually use more edges. Okay, so this is what the power of that is. This is where you get that extra benefit. Okay, so let's see, reset D of B to 24, and that you got to reset its alarm. So it used to be you didn't have an alarm at 24, and now you have an alarm at 23 and 24. At time 23, you process that alarm, you process D, you set D, you make sure it's 23, you process that. D of, now you found another path to B. You found a path from A to C to D to B, right? But the path from A to C to D to B is of length 23 plus 26. So it's longer than the path you've already found. Okay, so breadth first search would not go along that path, and we're not going to either. So we're going to keep the alarm at 24, and it's so because it's less than the new object we've discovered. So we leave it alone. Okay? At time 24, we process B, and this is the shortest path tree. The blue tree is the shortest path tree. And, we see that it's different than breadth first search in the sense that It's using hop 2 path, which is shorter than a 1 hop path. Okay? Okay, so you set, you're done. Okay, so this is alarm algorithm. Let's just write it down as an algorithm. Repeat until there's no more alarms. Next alarm goes off at time t. Let's just say it goes off at time t for node u. Then you process node u. You always process the next alarm, right? You don't process an alarm at 24 when there's an alarm at 23, right? We processed them in order. Okay, so for each neighbor of the node for which that alarm was associated, if there's no alarm for v, we set an alarm, because we've gotten to this node and we know there's a path there's a edge of length L of uv, and there's that many hops in the breadth first search algorithm. So the time at which you would reach that node through this node is t plus L of uv. So you set that alarm. If v's alarm if there is an alarm, if it's less than, there should be a less than then reset it to the earlier time. If v's alarm is greater than t plus L of uv, then you reset it to this earlier time. Okay, so this should have a greater than. Okay, so what's the implementation? So this again is a little bit, now we have to talk about how to implement alarm clocks and all those things on a computer, right? So breadth first search is kind of like picking it up from S, but we had to implement it with the data structure. So how do we implement this algorithm with the data structure? So what are the things we need to do? Let's look at the first step. You can set an alarm clock for node S. That seems easy, right? You just set it up. Repeat until there are no more alarms. That's just a loop construct. Next alarm goes off at time t. So that you need to find the next alarm. So you need to, in essence, what you need as a data structure, you need to maintain alarms for each node. Okay? And what are the two things you need to do? You need to find the next alarm. You don't want to find one way, you want to find the next one that you haven't processed. And you also may need to, in this step here, you reset it to an earlier time. If you already have an alarm for a node, you may reset it to an earlier time. So you have to set alarms for nodes. You may need to reset them to earlier times, and you need to find the one that's closest, has the lowest value. Okay, so now there's insert. So we're maintaining alarms, right? So for each node, we're giving an alarm value, which we call a key. And we're going to say we have this special command, which is called decrease key, which then you're going to set, if V may already have a key associated with it in your data structure. So you may have to reset that value. Okay, and then you want to delete min. So what you want to do is you want to find, just like in a queue, you want to take out the first element. You actually want to delete it. Every time you use a queue, you don't want to have the same element in there again. So what it does is it returns a V with the minimum key. It returns a vertex with the minimum key. Okay, so these are the sort of translating this word algorithm into data structures. Okay, so, and this is Dijkstra's algorithm. So let's see what it does. Okay, so again, it's just translated into code. For each vertex, you just set all the distances. That should be infinity. D of S is equal to 0. So let me just write that down. Okay, so initially, D of V is equal to infinity for all. Okay, so now what you do is you insert S, you set an alarm at time 0. Okay, that's what you do here. You set an alarm at time 0. Now, each time you pull out, U pulls out the next alarm from the queue. That's what this loop does. Okay, and now for each edge, it processes the edge. If you found a better path, so the distance of V is the last key you had for that item. And now, if it was larger than the new path that you found to that node, you reset the key to this new value. Okay? So what's the runtime? So how many delete mins do you do? You only process each node once, right? Once it's visited, you don't put it back in the queue. Okay? Because these nodes are coming out in order. You never discover another path to a node that you've already seen that's shorter. Okay? So, and you have V inserts. Every time you see a new node, you may put it into the queue. And what else do you have? You have, each time you do this operation here, where D of V equals du plus L of uv, you need to decrease the key. Okay, you need to reset the alarm on that queue to decrease the key. Okay? So this resetting of the distance label also comes with it, is you need to decrease the key because you've changed the alarm structure. Okay? So the binary heap takes this amount of time, and so the total running time is this. And I'm going to give you a break, and then we'll discuss the binary heap and D-array heaps and how that affects the running time. So here, the one thing to notice is that E may be much larger than V. Okay, that's because and the reason and this data structure really does more decreased keys than anything else, because each time you process an edge, you may decrease a key. So maybe we can change so we're going to look at this data structure, and we're going to see if we can optimize it to take advantage of the fact that we do many fewer delete mins, typically, because V is always going to be not bigger than E, usually. E could be as big as V squared, right? So E can be very large compared to B. So you want to make sure that you want to see if maybe you can mess with the data structure a little bit to make it cheaper for decreased keys. Okay, so we'll do that after a break. So we're going to try to show how to do all of these three operations in log n time. Okay, and then I'm going to show how to trade off the expense of these operations, make them more expensive in exchange for making these operations less expensive, because there's more of these, right? So this is a game we play, to try to, get the common stuff cheaper, right? Okay, so you want to optimize the common case. This is just sort of a thing. So this is a heap. So the heap property is basically a tree, and each node has two children. In this case, it's a binary tree, so each node has two children. And the heap property is that each of the children are bigger than the parent, okay? Or the parent has a better value. Okay, so 3 is bigger than 9 and 5, 5 is bigger than 11 and 6, 10 is bigger than 11 and 7, 11 is bigger or tied with 11 and 15, and 9, right? So at every node, you can check this condition. You just check their children, and you see if they're both at least as big. Okay? Does that make sense? Okay. And there can be ties, because in fact, in the breadth first search algorithm, there will be ties. Right? There might be two nodes that are reached at the same time. So it sort of doesn't matter which one you process first. They're at the same level in the breadth first search tree. Okay? So I'm inserting 7. So how do you insert? One of the things I want to do is insert, I want to delete, and I want to decrease key. So when I insert, this one shouldn't have been there before because I hadn't inserted it yet, but now I'm inserting it. And now what I do is I put it at the bottom. So what's the problem here? Yeah, so what is the problem? What is the problem? Anybody see a problem here? What was the heap property? Is that the parent is bigger than the children. So do I create any problems here? No. Do I create any problems here? No, it's nice. This is really nice because it only creates a problem in one place. Right? That's what's nice about this. Is this property is very, very local. Okay, I look at a node and I look at its children. Is it a problem? Okay, so if I only put in one child, there's only a problem in one place. Okay, so how would I fix it? Is there a way? Do you guys see how to fix this problem? Yeah, you just swap them. Okay, well that's not a problem anymore. But what have I done? I've moved the problem up one level, right? So now 7 is smaller than 9, and 9 was supposed to be smaller than both of its children. Okay, so I swap it. And now is there a problem at all? No problem. Okay. And now what was the expense of this? What was the algorithm? Each 7 just checked its parent. Now the parent didn't have to check both of its children. This kid's still good. Right? He's nice. He's the good kid. Right? He didn't have to check this kid. The kid just checks with the parents and takes the parent's place. Okay, so that's all. But it's only the kid that checks against the parent. The other kids are good, and once he swaps, does he need to check against the other kid? Well, because the parent is less than the other kid, and he's less than the parent, so he knows he's less than the other kid. So he doesn't need to look at the other kid. The other kid is truly the good and ignored child in this algorithm, right? Okay, so what's the number of comparisons? Now, I'm going to do the constant factor here. I'm going to say the number of comparisons is at most the depth. Okay, that's a real upper bound, no asymptotics here. The depth of this tree is an upper bound on the number of comparisons. It's not O of the depth, it is the depth. Okay? Okay, now for delete min, what do you do for delete min? Well, what's the smallest key in this tree? Where is the smallest key in this tree? It's at the root, because it has to be bigger than both of its children, which are in turn the smallest keys in their subtrees. Or it has to be smaller than each of its children, which are in turn the smallest nodes in their subtrees. Okay, so what you do, first you delete it, right? Because you take that 3 and then you use it in your algorithm and you delete it, so it's gone. But you need something at the root, right? You can't just have no root. So you replace it with any one of the leaf nodes. Okay, so now now I have a tree with one fewer node in it. And, it looks good in most places. Where isn't it good? Yeah, it's where it's colored red. That's kind of a clue on this one. So, okay, so 10 is bigger than, in fact, both of its children. Okay, so 10 is bigger than 7, so should I switch 10 with 7? Yeah, I shouldn't, because then 7 is also bigger than 5, and now I have problems in 2 places. If I switch 10 with 7, there's a problem here, and there's a problem with 7 and 5, right? So what I should do is I should check for 10, there's a problem, so he has to look at both of his children. Okay? And he switches with the smaller of his children. Okay, so now if I switch with the smaller of the children, now if I switch 5 up here, is there going to be a problem with the other children? No, he's the smallest child. So 5 is going to be smaller than 7 for sure. He never needs to compare himself to 7. 10 already this was the smallest child, so it's smaller than all the other children. Okay? So it was important for 10 to really pay attention to his children here, both of them, right? And pick the better one. Does that make sense? Yeah. But your parents lied if they said they love you the same. So I'm kidding. Oh. Okay. So then you're here, and now what does 10 have to do? Look at both of its children. Okay, it compares this 11 and 6. Okay, so there's no rhyme or reason to this. It's not that the right child is smaller than the left child. You really have to look at both of your children. Okay? Because this heap property is pretty weak. These things are not sorted in any way. They're just really, they have this very local property. Okay? So now, what's the total number of comparisons? Well, it's at most 2 times the depth. At each level, you compare to both of your children. So this 2, normally with asymptotic notation, we don't really pay too much attention to 2 because we're talking about running time and computer operations. But here I'm counting precisely comparisons, exactly how many comparisons are there. Once I count comparisons, I can do this quite reasonably. I can actually say what's the constant factor. Okay, so it's 2 times the depth. Okay, so now what's the depth of this tree? What's the depth of the binary tree at most? Log base 2 of n. What? It's log base 2 of n plus 1. It's always at most log base 2 of n plus 1. Right? Because you can say it's log of, you just take the next smaller power of 2, which is an factor of 2. That's log n. That's the most log n plus 1 for this next level. Oh yeah, you need to actually say it's a balanced tree. Yeah, so that's right. So this is what I did to insert. So when I insert, what did I do? I didn't insert this anywhere. I set it at the next empty leaf. Okay? If I always, and then the next place I'm going to insert is here, and the next place I insert is here, and the next place so it's always going to be balanced. Right? This is why a heap is way simpler than a balanced binary search tree. Okay? It's way simpler because I don't need to maintain that these things are sorted. They're totally not sorted. But I could still keep this heap property. Yeah. Outside. Yeah. It's just ceiling. It's a ceiling. So okay, so this maintains it. With the binary search tree, it's pretty hard, right? It's really a process to make sure that the thing is balanced. But for heaps, it's all very simple. You just stick it right here. Okay? Okay, so see bubble up, check. Okay, so there's my fancy graph. Yeah. That's fine, yeah. We need to have that for priority queues. Why? Because we're using them for this. We're using them for Dijkstra, and Dijkstra, 2 things may really be the same distance away, right? So if they're the same distance away, they're going to have the same key inside the priority queue. So it's less than or equal to, right? You can't ensure that that the children are bigger. They're bigger or equal to. Okay. So okay. So now. So this is going to be log base 2. Now I can replace this with a d-ary heap. So there's a degree d. Okay. So now notice that the expense of inserting is the depth. And when it's degree d, the expense of deleting is you need to check all your children. Now, how many children do you have when it's degree d? Well, d, right? So now when you use d as a variable, this 2 becomes d, and it's no longer just a constant. Okay? So, but if the degree is d, what's going to happen to the depth? Is it going to, with a higher degree tree, is the tree going to be deeper or shallower? Yeah. So the depth is, by raising the degree, you decrease the depth. So you absolutely decrease this running time of inserts. By raising the d, you increase the running time of delete min, because you have to look at all your children. Okay? So now, this is the kind of trade-off that we should do, we should understand in computer science. If you do more of one kind of operation, how do we make that operation cheaper, even if we have to do more work elsewhere? Okay? If this is our bottleneck, we need to see how to make that one be less. And this insert and decrease key is the same thing. You're bubbling up, right? Insert and decrease key have the same complexity. It's just what you do when you decrease a key is you create a violation. And you decrease it. Since you only decrease it, you only bubble up, you only need to look upward. So inserts and decrease key only have complexity depth. Making the depth smaller is a good thing. Making the degree of the tree bigger is a good thing. So that's just the intuition. So now I'm going to do a little bit of algebra, which is always less fun, but okay. So if the degree is d, the depth is log base d of n. Okay, this is sort of like the master's theorem. It's just the depth of your recursion, right? So now insert and decrease key, log base d of n is the same as log n over log d. Okay, this is just how logs work. Now delete min goes up, right? It's d times the depth. The depth is log n over log d. Okay? So because, and the factor of d comes from checking all your children. Okay? So now Dijkstra becomes, well, there's order v delete mins. Every time when you process a node, you delete the min. And there's d log n over log d of those. I mean, each one costs that much. There's order E, insert or decrease keys. And those cost log n over log d. So the total running time is this sort of nasty looking thing, which, you know, if you choose d to be the average degree, which is kind of funny, the degree of the tree is going to be the average degree of your graph over 2, then the running time becomes this. So you improve the running time. The previous running time was order E log n, assuming E is larger than D, which you could always assume, essentially. Okay? So if E, it's order E log n, so we get a log D speed up. Okay? And now, for dense graphs, for graphs where E is around n squared, right, if you have like a complete graph, if you know the distance between all the pairs, or some distances between all the pairs, or some relationship between all the pairs, it becomes linear time, because D is going to be around n. So you get order E times log n over log n. Okay? So for dense graphs, this is a pretty good algorithm. But they have to be pretty dense. D has to be pretty large for you to get much of a benefit from this. Okay? So there's these other heaps called Fibonacci heaps, which have some nice properties. Again, they're log n per delete. Each delete costs log n. There's order 1 average decrease key cost. So they're kind of very fancy heaps. They have the heap property, but what they do is they make it so, you know, this bubbling up process. So we have this bubbling up process. So in the worst case, this bubbling up process bubbles up all the way up the tree. So a Fibonacci heap says, well, on average, I'm not going to bubble up that high. It just hopes and hopes and prays that that happens. And somehow they make that happen. Okay? And the intuition is, you know, it's really beautiful, these analysis, but I won't go into it. But a little puzzle is, say I add a number 1. Okay? I add 1 to a number over and over and over again. Okay, so how far will the carry go? In the worst case, if the number is all 1s that I'm adding it to, if I have this representation, 1, 1, 1, 1, 1, 1, 1, and I add 1 to it, how far will the carry go? A long way, right? But if it's a typical number, I'm going to have 1, 0, 1, 1, 0, 1, 1. How far will the carry go? Not very far. With probability 1/2, if it's a random number, with the probability 1/2, this is a 0. So the carry only goes 1. As soon as I hit a 0, the carry only goes that far. So this is an example when you add 1 to a number over and over again, each operation, there could be an operation that takes order B. But the average operation takes order 1, right? So this is an example of something where if I add this 1 to something, I'm going to usually only wait 1 time step because the carry won't go very far. On the other hand, occasionally I'm going to pay a lot. And that's what this Fibonacci heap has. It has the same sort of property. So usually the decreased keys don't cost much. You don't bubble very far up the tree. Okay? But occasionally you go all the way up the tree. Occasionally you get this big disaster, okay, where you have to change everything. Okay, this is the way this data structure works. Now, and with that, you get linearity. So in this case, you get that, well, each delete costs you log v, and on average, all your decreased keys only cost you order 1. Okay? And then this is a very efficient algorithm. The log v does not multiply e at all. So even for moderate, even if the graph only has sort of mildly, has a few more edges, essentially, log v edges per node, it's linear. Okay? So we'll do more path problems.